In today's video we're going to talk about negative cyclic and periodic homology. So in the analogy between Hochschild homology corresponding to the de Rham algebra, the Kohn operator corresponding to the differential, in this analogy periodic homology corresponds to de Rham cohomology. We'll introduce these terms, make that precise, and compute periodic and negative cyclic homology in some examples, for example in the case of Fp relative to the integers. Hi, I'm Thomas Nikolaus from Mathematik Münster. And in order to talk about periodic and cyclic homology, we use the same conventions that we always use in this video series. So R is going to be a K algebra, where K is some commutative ground ring. And in this situation we have the Hochschild complex HH R relative K, and that is the chain complex over K. And it comes with a Kohn operator, which we denote by B, Rk to HH R relative K shifted by -1. So this is a homological shift by -1, and as always we'll use homological conventions in this lecture. Okay, and another way of interpreting or expressing the existence of this B is to say that HH R relative K is canonically a DG module over the DGA, over the DG algebra, which we call A, and which as a graded commutative algebra is just ZB mod B squared. B is in degree 1, and we want to equip it with a zero differential. So it's a formal DGA, but nevertheless, of course, it can act on a chain complex in a way which takes into account the chain complex differential. So it's a DG module over that. And so we want to say Hochschild homology R relative K is a DG module over A. And at several points already in previous videos, but also today, we'll sort of do derived functors in this category. And in order to express this, because there is some potential for confusion, as I wanted to write, sorry, I made a slight mistake here. I want to write K. I work over K here, sorry. I always have the case in mind where we work over the integers. But sort of in order to express the homotopy theory or derived functors, the derived tensor product and the X groups and so on and so forth, the homotopy theory that we will use here is the one where we invert the quasi-isos so the level-wise quasi-isos, right? So we take this category and formally invert the quasi-isos. And at the moment, I mean, we just use that as a black box. Basically, we just talk about derived functors, but later this will of course be the infinity category of A modules in the derived infinity category of K. Right, but again, for the moment, the point is just that we consider two objects equivalent in here if there's a map of A modules, which is an underlying quasi-iso of K modules. Okay, good. And now with this notation and these conventions, we can define cyclic and periodic homology. So the cyclic homology of R is the following. It's denoted HC star R relative K. And this is just the homology of the chain complex, which is given by taking K. We consider K as a module over A by the augmentation map, sending B to 0. So this is the right module over A, and we take the derived tensor product over A with the Hochschild complex R relative K. So this is the left module over A. The derived tensor product will just result in a chain complex over K. Doesn't have an A module structure anymore, right? We tensor left and a right module, and then we take the homology of that chain complex. And another way of writing that is just to say it's the Tor groups of A, K, H, H, R relative K. But again, I want to issue the warning that Of course, this is Tor groups where this is the chain complex. So one has to be a little bit careful what exactly one means by Tor groups. I mean, the potential for confusion comes from the fact that this a priori doesn't have a differential. So it could be considered as a graded algebra, and you could work in the derived category of graded Abelian groups. But having said this, we don't do that, so forget about it immediately. We work in just the G modules, and that's a derived tensor product with a Tor there. Okay, that's the cyclic homology. And in fact, the cyclic homology will not play any role in this series of videos at all. I just introduced it for completeness. The more important invariant for us is the negative cyclic homology. Negative cyclic homology of R is HC star minus R relative K, and that is just defined as the homology of the derived hom, R hom over A from K into HH R relative K. And again, the derived hom is the chain complex, and we take its homology. And this is, if you want to stick with this Tor notation, then the corresponding notation here would be X. And let me write minus star, because X is usually homologically graded, but again we use homological grading here. So this would be X from K into HHR relative K. Okay, that is the negative cyclic homology. And again, this is going to be for us the more important invariant than cyclic homology. And confusing thing is, and this will hopefully become clear in the course, that what the main topic of this course, topological cyclic homology, is not an analog of cyclic homology. It's more like an analog of negative cyclic homology. But we'll explain this later. So the name topological cyclic homology is a little bit of a misnomer. Anyway, I'll talk about that later. So one thing to observe at this point now is that given that the negative cyclic homology is like an X group on R hom, this is a module over the X group from K to itself, Xa star from K to K, right? Or in other words, the homology of R hom A K to K, right? It's just X by the composition product, but this actually is isomorphic. The homology groups are isomorphic to K adjoint T, where T sits in homological degree -2. And that is a little computation which I will want to post as the next little exercise in our course. So at this point, it's a very good exercise to just pause the video and try to compute why this is true. And again, this involves not getting confused about the possible different meanings of what this X group means. So again, you have to replace, one way to do that is to replace K by something quasi-isomorphic, which is flat over A, and then just computing the chain hom. Okay. I hope some of you have been able to complete this exercise. And now that we have this operator T, in particular we have an element T which acts on the homology of the on the negative cyclic homology, and that allows us to define the periodic cyclic homology. The periodic homology, sometimes called periodic cyclic homology, but for brevity I'm just going to write the periodic homology of R is the following. It's denoted HP star R, and this is just the negative cyclic homology R relative K, and I invert the element T. Right, this is a graded module. I have an operator T acting, and I can invert this object. It's just a filtered colimit of multiplications by T. Okay, that is a periodic homology or periodic cyclic homology. And at this point, I have just introduced the groups, cyclic homology groups, negative cyclic homology groups, and periodic cyclic homology groups. But of course, there's also the complexes. And similar to our notation for Hochschild homology, we'll just, if we leave the star away, we just mean the complex, and that is just going to be this complex. If we leave this star away, we're going to mean this complex. And if we leave this star away, we're just going to mean the localization of the negative cyclic complex at the variable t. Okay, which has homology exactly that, because localizing commutes with taking homology, which is a filtered colimit. Okay. And now some of you might have seen different definitions of cyclic homology, negative cyclic homology, and periodic homology, especially if you look at the standard literature about the field. For example, Laudet's book is a really good source for this. Then you'll find a definition in terms of a double complex for cyclic and negative cyclic and periodic homology. And one can wonder how this connects to the definition that I've just given. And the connection is the following. Proposition and that is for any K algebra R, we have that the negative cyclic homology, and now again here this means the complex, negative cyclic homology complex. This is quasi-isomorphic to the complex, or by definition this is only defined up to quasi-isomorphisms, right? I mean, it involves deriving, so maybe this is the best thing you could possibly say to the following complex. You just do Hochschild homology R, that's a chain complex, but I ignore the fact that it's a chain complex. I consider it as a graded abelian group, and I adjoin a generator T, a power series generator in degree -2. Right, in other words, this is as a graded abelian group just an infinite product where for every further copy of T I shift down by 2. And then I equip that with a differential which I denote partial plus TB. Where, what do I mean by partial plus TB? Here, partial plus TB is defined as this is supposed to equip this graded abelian group with a new differential, so as to make it a chain complex. And how is it defined? It's defined, I mean, I guess I have to tell you what it does with elements x t to the I for x in the Hochschild complex R. Right, that are the generators here. And how is this supposed to go? It's supposed to send this to, I guess, partial x times ti. So this will also have the property, maybe I should have additionally written that here, that partial of t is 0. So it's going to be partial xi ti plus bx. So here, this is the second term times t to the I plus 1. Well, that's what I mean by this suggestive convention. You just think about this differential, and you also declare that the differential vanishes on t, and think about what the product rule would give you. Okay, so that's this complex, and similar we have a description of the periodic complex R relative K, and this is then along the same lines given by HHR round brackets T, so the Laurent power series, and then partial plus TB. Same differential, except now we allow negative powers of I. Okay. That is the statement, that this is the way you can compute, and if you spell out what that actually means, you can write that in a double grid as a total complex of a double complex, and then that will exactly be the standard way very often you see the definition of cyclic and periodic homology. And let's prove how that relates to our definition. Okay, so the idea, let's remember what our definition was. Our definition was that we had to form a derived HOM. So what we have to do is that we have to resolve K as an A algebra by the following resolution. I'm just going to define for you an A algebra C, and that's going to be a DG algebra over A. And as a graded module, it's just going to be a free A module on generators x0, x1, dot, dot, dot. This is just supposed to mean the free A module on this basis. And the generator xk is supposed to sit in degree 2k. And how am I going to make this into a chain complex? I'm just going to declare that the partial of xk is equal to b times xk minus 1. So what's the element b? The element b is the element in the algebra A. Recall that A was k adjoint b mod b squared. Okay, and now again, this is just going to be a resolution of k as an IA algebra. It's a little claim, so I guess at this point, again, if you've done the last exercise, this should be fairly obvious to you, but if not, then again, here's the chance to pause the video and verify that this is true. And in fact, this is a co-algebra. This, and by this I mean C, is a co-algebra with, I guess, co-unit sending x0 to 1 and the rest to 0. And with co-multiplication delta of xi is given by the direct sum m plus n, maybe I should write xk, and this is I plus j equals k, xi tensor xj. Okay, that gives us a co-algebra structure, which will be relevant for why I write this as a product. I'll explain a little bit what the significance of this co-algebra structure is in a second. For the moment, we don't really care about the fact that it's a co-algebra. We just need to resolve it as a DG module. And then we get that the R-hom that we need to compute in order to get our negative cyclic homology from K into a Hochschild complex R relative K, that this R-hom is just computed by the inner hom in chain complexes over A from just this resolution C into HH R relative K. Right, but what is this now? Now this guy is actually free on this basis of xi's. So this is, I mean, giving a map from C into Hochschild complex just amounts to giving elements corresponding to the xi's. And this is what we'll just record. This is as a graded module, this is just the Hochschild complex of R bracket T. Where here T to the I is the dual, maybe I say that in word, T to the I is the dual, the image of the element xi. T to the I is the dual of the element xi. And now you can work out what the inner hom complex has as a differential. So if you remember how the inner hom complex is defined, the differential is the sum of the two differentials, the differential here and the differential here. The differential here is just the B operator. That gives me the term TB. Right, and what is the differential here? The differential here is just going to be, the differential here was the partial operator. That gives me the term partial. Sorry for that. And then the differential here was just, let's look it up, it's just given by B. But because this is an A-linear map, the B will be sent to the B operator here. And here the differential lowers the k degree by 1. So as a result, it will increase the t degree by dualizing by 1. So this differential is TB. Okay, that gives you this formula, and there's no signs because t is even. Otherwise, I guess you'd have to contemplate for a second what the sign would be. Okay, so that's a computation. That gives you this statement. And that proves the first part, namely that this is a complex computing this R-hom, which was our definition of negative cyclic homology, and then the formula for HP follows by localizing at T. So you just have to localize this complex at the variable T, and then you can pull the localization in, and if I take a power series algebra and localize at C, I get the Laurent series algebra. And of course, there's one little catch, namely that this t is the same t as in the definition. But if you've computed this X algebra, if you've done my last exercise, you'll know why. Because one way to compute this X algebra and get the t is by using the exact same resolution. And maybe one could object that this only determines t by a unit or something, but this doesn't matter here because I guess localizing in an element or a unit multiple of it doesn't change. Okay, good. That proves this claim. And now I guess there's a bunch of remarks in order, especially remarks related to this mysterious coalgebra structure. But before I talk about this coalgebra structure, let me just remark that this formula works more generally for any DG module for any object, let's call it H, in DG modules over A, to give the R hom over A from K into H. Right, so in general, if I have such an H in place of HH, this exact same formula, where now partial is the differential in the H, will give me a formula for this R hom group. And this is an important observation that we'll take advantage of in a second. But first I want to say a bit about the product structures. Okay, so what about this mysterious co-multiplication and product structure? So after all, I've written this formula in terms of a power series variable t, suggesting some sort of product structure. And if you want to make that rigorous, you first have to observe that A is a Hopf algebra. In the following way, I guess I declare a co-unit from A to K to send epsilon of B equals 0, and it's k-linear. That determines it, and I want to declare a co-multiplication partial from A, a delta, from A into A tensor A, and I declare this to satisfy the relation that B is primitive, plus B tensor 1. That gives me a co-algebra structure, and so in order to make sense of the fact that this resolution was a co-algebra over A, I first of all need to have a tensor product over A. And so in fact, in order to say this is a co-algebra compatible with A, I already had to use that the category of A modules has a tensor product, and that is exactly induced from this co-multiplication or from this co-algebra structure in A. And I guess this also means that this R hom over A from K into black is the Lax symmetric monoidal functor. Lax symmetric monoidal functor. Right, because that's generally true that, this is in fact the tensor unit in the category of DGA modules. So mapping out of the tensor unit will always be a Lax symmetric monoidal functor. More generally, mapping out of a co-algebra will be a Lax symmetric monoidal functor. And as such, it is given by this chain complex H brackets T partial plus TB. Right, this is also the thing which sends H to this term is also a Lax symmetric monoidal functor. And this explains where the multiplication in the T comes from. And what we've really proven is that this as a Lax symmetric monoidal functor is equivalent to that. Okay, and so what is this bias? I guess maybe some of you are not used to thinking about Lax symmetric monoidal functors. This in particular means that if C is a algebra object in DG mod A, so I guess again at this point if you're a little bit confused about the definitions, I mean, I admit that I'm always confused about these things. It's very good to pause the video again and just figure out what does it mean now that C is a DG algebra in this category. Okay, I hope some of you could solve that. I mean, it's basically clear, but I mean, you know, clear on the level where once you sit down and figure it out, it's obvious, but things might get confusing. Then that means that B, I mean that C is a DG algebra, DGA, and B satisfies the Leibniz rule. The Leibniz rule? So then, what does the lag symmetric monoidal structure buy us? Then, from the fact that this functor is lag symmetric monoidal, we get that R hom A K into C is a DGA. Right? So that's what it tells us. And as such, it is now equivalent to the DGA where I put C brackets T in partial plus TP. So that's the real content of what this whole co-algebra, co-product structure is about. And maybe I admit that this was an overly fancy way of saying something somewhat simple. But the problem here is that this is never the case in practice. Okay, let me tell you what I mean by that after wiping the board. Problem. Even if R is commutative, then B is not is not on the nose derivation on HHR. So recall, if R is commutative, then Hochschild homology, or the Hochschild complex, inherits the structure of a CDGA, in fact, coming from the shuffle product. And one could hope that the B operator, the way we defined it, is actually compatible with that product structure. This is unfortunately not the case. I think I've mentioned that earlier in my last video, but I have to mention it here again. This is not a derivation. So we cannot apply this abstract observation to deduce that negative cyclic and periodic homology are just products. Now, there is this fact, which I've mentioned last time briefly already, that this is true, but this is true up to chain homotopy. Right, so what I'm saying is the Leibniz rule fails on the chain complex level on the nose, but it is witnessed by a chain homotopy. And this is still not enough, if you think about it, to deduce that negative cyclic and periodic homology is again equipped with a ring structure. So we'll see later that in fact this is true up to coherent homotopy, this Leibniz rule. There's a lot of subtleties arising from formality of this algebra A. So really you want to put chains on S1 and stuff like that. And I think at this point we don't have the expressive power to even start contemplating these problems. So for the moment I just want to use the hack. I observed that there's no a priori reason why this R hom would actually be, if C only satisfies the Leibniz rule up to homotopy, there's no a priori reason, if you think a little bit about the homotopy theory, why this R hom would actually be an algebra. But we have this formula. And if you just stare at this formula, you see that still this is actually going to be equipped with a product up to homotopy. But hack, I again want to say this is just a hack, and we will sort of resolve that better later, and sort of, yeah, we'll talk about that later if we have the expressive power. But this is still enough to deduce that this term, HHR brackets T, with this differential partial plus TB, has a product up to chain homotopy. i.e. that HC star minus R and HP star are graded commutative algebras. Okay, good. So that is the takeaway that I want to do from this discussion, which at this point necessarily has to remain a little bit mysterious. The takeaway is that if R is a commutative ring, then HC star minus and HP star are actually commutative algebras. Okay, good. Okay, so now we want to enhance our HKR theorem that we talked about earlier in this series of lectures. Recall the HKR theorem relates the Hochschild homology and the de Rham complex. And the point is, the upshot of periodic and cyclic homology is that periodic homology in this correspondence corresponds to the de Rham cohomology. So to make that precise, let me first define what de Rham cohomology is. So R, again, now a commutative K-algebra. Commutative K-algebra. The de Rham cohomology of R relative to K is defined as the de Rham cohomology R relative K, and it's the obvious thing you would do. You would just take the homology of the de Rham complex. Just take the de Rham complex. I mean, it's pretty much like, you know, from differential geometry. Just take the de Rham complex, R relative K, and you take the homology with respect to the de Rham differential D. That is the de Rham cohomology. And immediately want to issue one little warning that this is basically boring. Boring invariant. So here I only allow R to be a commutative algebra, and this is, I mean, in the language of schemes, which I will talk about in a little addendum or companion video to this lecture. I will sort of define all these invariants for schemes instead of only affine schemes. And in the affine situation, typically de Rham cohomology is boring. It's actually very often contractible. And really, we care about the non-affine situation. But for simplicity, in this lecture, I'll stick to the affine situation. So you should take everything I say with a little grain of salt. So somehow, really, these are like just role model theorems for the actual theorems we care about, which we will talk about in this companion lecture. So what I'm saying is that H star de Rham can be defined for schemes X over K. And then this is going to be the invariant we really care. Then we have the de Rham cohomology of X relative K, which reduces to this definition in the affine case. Okay, good. So that's the definition. And here's the theorem which relates the de Rham cohomology to periodic homology, and that's my theorem A today, main theorem in today's lecture, or the first main theorem. So now for this I will assume that Q is in K. Q is in K, so we are in a characteristic 0 situation. And I will make the same assumption that we made for the HKR theorem, namely that the cotangent complex L R relative K is flat dimension 0. We didn't talk about the cotangent complex. This just means, and we will have later lectures about the cotangent complex, this just means that the cotangent complex is, this is a priori a complex of R modules. It's concentrated in degree 0 and they are represented by a flat complex. And think about the case, this has as a special case the case where R is just a smooth K algebra or a regular K algebra. So you can just think about these cases. Worst case, think about a polynomial ring. Okay. And then the conclusion of the theorem is then there are natural isomorphisms as follows. So the periodic homology HP star of R relative K, so this is now commutative algebra by our graded commutative algebra by our previous discussion. This is naturally isomorphic to the de Rham homology of R relative K, except it's going to be a two-periodic version of that. So we adjoin this variable T. Right, so remember in the definition of periodic homology we've already inverted some T. So this necessarily is two-periodic, the de Rham complex is not, but we can easily make both two-periodic by adjoining this variable to P. This is just, so if you spell out what that means, it's just a two-periodic version of the de Rham homology. Okay, so this is the first theorem, and the second one is that negative cyclic homology is a sort of truncation of that. And maybe, I guess the easiest way to express that is to say in degree n, this is given by the de Rham cycles, Zn de Rham, R relative K. So what I mean by that, this just means, I take the de Rham complex and I take the cycles in this complex in degree n. In other words, closed forms of degree n. But I don't quotient by boundaries. That's the difference to saying Hn. And then I have the direct product I larger equal to 1 of the de Rham complex n plus 2i of R relative K, or the de Rham homology. So basically these are products indexed by T. So the way this maps to that is just the way where somehow this product is really by powers of T, and this cycles just map to the cohomology group, right? So it's a very easy to observe that if you take this guy, maybe it's better to index those by powers of T. Then it's a very easy exercise to prove that once you localize this guy at T, you get this guy. Just so that you get, this is not injective, but it's like a truncation, except here on this level you don't quotient by boundaries. Okay, so that's the main result I want to prove now. And before I do that, I again want to make some remarks. So again, this is essentially a boring statement. Especially if you think about the case of polynomial rings, it turns out that if you take a polynomial ring over Q, that geometrically just corresponds to affine space, and the de Rham cohomology of affine space, of course, by a version of the Poincaré lemma is trivial. So this very often is the statement 0 equals 0. Again, this is just a model statement. So the real statement we care about is the statement that if X is a scheme, and again, don't worry if you're not so familiar with the language of schemes. We'll explain that in a companion lecture, but it will not be relevant, really relevant for this whole course. So this is just because it would be a little bit of a left out to just make a trivial statement. So for a scheme X relative K, which locally satisfies the same condition, so where the cotangent complex X relative K is flat dimension 0, we have a similar isomorphism And that is the real theorem, which we'll prove in our companion, which is that the periodic homology X relative K. And here, a priori, we have only defined periodic homology and Hochschild homology for rings. In particular, we'll have to say what that exactly means. Then this is isomorphic to the two-periodic de Rham cohomology. Okay, so that's the first statement. And the second statement is actually, now at the moment I have a smoothness condition here. So I assume that the cotangent complex is flat dimension 0. That's maybe what in Badmoro-Scholze is called quasi-smooth. And so one can in fact drop all smoothness conditions on R over K if one is willing to replace the de Rham cohomology here by a certain variant of that, which is a Hodge-completed derived de Rham cohomology. In order to talk about that, we'll later have to talk about non-abelian derived functors and the cotangent complex, then we'll make a more general statement along these lines. So the smoothness is basically just in order to make this a invariant which is more classical. But there is a statement without smoothness, at least under some quasi-symptomic assumptions. Okay, so this is this statement. And secondly, for both of these statements, it's very crucial to work in characteristic 0. So these statements are plain false if characteristic K is not 0. So for example, if we work over the integers, these statements are just plain false, or if you work over any ring of characteristic P. And after talking about this rational case, we'll see that in this kind of positive characteristic or mixed characteristic case, this will actually only give a spectral sequence, the same arguments. We'll talk about that in a second. Okay, so now we want to prove our theorem, namely that periodic homology in characteristic 0 is basically two-periodic de Rham cohomology. And in order to do that, there's a bunch of proofs. Later, when we talk about non-abelian derived functors, we'll give more fancy and more highly structured statements. But there's a very classical proof of this fact, which I believe is due to Kohn. I learned it, I guess, from Lode and from lectures of Husemöller and others. So what we do is we consider the following map. We have the chain complex, Hochschild chain complex R relative K. And what I want to do is I just want to write down a concrete chain level map from Rk into omega n R relative K. And by the way, remember that a priori we have to resolve here by DGAs and so on and so forth. But the convention in this course is that we're basically ignoring that. Because that just, the claim is that all the formulas work similarly but get more annoying. So in order to, I guess, save myself some effort, to be honest, and also to save you from having to get confused or possibly getting confused by all these different indices and directions and conventions, I'm pretending everything is just ordinary rings and we don't have to resolve. Okay, so here we're going to write down this map, and so it's supposed to go from the nth layer in the Hochschild complex. Remember, this nth layer was just R to the tensor n. Right, there was the nth layer in the Hochschild complex, and I guess if I write in n here, I have to be a little bit careful. The Hochschild complex starts with this, so I guess I have n plus 1. So it starts with R. And how is this map defined? I'm just going to send R0 tensor dot 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 tensor Rn. And this is just mapped to the following term, 1 over n factorial R0 dr1 times drn. Okay, good. So this defines a map. First of all, 1 over n factorial makes sense because we made this characteristic 0 assumption. So you see this is very crucial here, and we really can't get away with inverting certain primes. Right? I guess if you somehow, for some reason, only care about the first few layers in your Hochschild complex, or said differently, you restrict yourself to rings or schemes which have a certain bound in dimension, you can get away with only small primes being invertible. And I mean, there are theorems along these lines, but to get everything, we just need all primes to be invertible. So we need to be rational. And I mean, this term is obviously multilinear, so it's okay to define that on elementary tensors. So that divides me a map from the n plus first layer of that complex to this group. And the crucial observation is now that this is a chain level map. And more is true, this lemma says this is basically compatible with all the structure you can think of. So this is a map of CDGAs. GAs. What does this mean? So the left-hand side is equipped with the structure of a CDGA. It has a shuffle product and it has a differential partial. So I guess I say this is HH R relative K. This is a graded commutative ring. It has a differential partial. And I'm saying this map mu is compatible with this. It sends this guy to omega star R relative K. And now what differential do I pick here? The claim is I take the zero differential here. And additionally, besides being a map of CDGAs and A-linear. So what does this mean? This means here I have this con operator B, which gave me the structure as a module over this. So I have this partial and this B. This is, by the way, what is called a mixed complex in the literature. And then here I put the de Rham differential D. Okay, so the claim is it's compatible with everything you can think of. And again, there's a little bit of a catch here. I'll prove that result in a second. There's a little bit of a catch here, namely that, again, these two structures here are not really compatible with each other. So this is not a derivation on the nose, but we've seen that this didn't matter for everything we did, for all formulas we wrote down. And so the claim is that here they are, but that doesn't matter. So there's no, I mean, if you're a homotopically inclined person, you might think, well, maybe the B is somehow a derivation up to coherent homotopy. And then you'd somehow hope that this is compatible with the coherent homotopies here being zero. And in fact, one can prove that this is the case, but we're not going to prove that here. And we don't care at the moment. I mean, of course, we deeply do care, but not at this point. Okay, good. So that's a lemma. And let me give you the proof of this lemma. And as usual, I'll do the easy part and let you do the hard part as an exercise. So let's see, what is the easy part? So let's work out what mu of partial. So what do we have to check for this guy? We have to check that this is actually zero, right? We want to say if we first apply the differential in this chain complex and then the map mu, then this is the same as first applying the map mu and then the differential here, but this is zero. So we have to show that this term is actually zero. So let's work out what this term actually is. So what was the differential in this complex? The differential in this complex was this alternating sum, this thing where we put the Ri's on a circle and multiply adjacent guys together with signs. So this is just going to be mu of the following term. First we had this R0, R1 times R2 tensor dot 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 tensor Rn. And then we have minus R0 tensor R1, R2, tensor dot 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 tensor Rn, and so on, dot dot dot. And then the last term, we had the term where the Rn came over. So we have the term plus minus Rn times R0 tensor R1 tensor dot 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 tensor Rn. Okay, sorry, Rn minus 1. And now we have to apply the mu to this, right? So what do we get? So if we apply mu to this, we get the term where we have, the first term is R0, R1, and then we have dR2 times dot 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 dRn. That's the first term. What's the second term? The second term, we have minus, and then we get R0 times dR1, R2, dR3, dot 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 dRn. Right, and now actually, maybe I sort of do this three-dimensional board work. Well, I guess it's two-dimensional. So I'm going to continue here in a second. And so here actually, now we expand this out by the Leibniz rule. What does this mean? So by the Leibniz rule, we get that this is actually the term where we have R0 times dr1 r2 plus times dr3 drn plus an additional term, maybe I just copy this term, plus an additional term which is given by I guess I got that wrong now, sorry for that. So I guess I wanted to write R0, R1 times R2, sorry for that, this was just the wrong Leibniz rule. Okay, R0, R1 times this term, and then the next term I get is going to be R0 dr1 times R2, I guess I pull out the R2 here, R2 dr3 drn, and then plus further terms and plus further terms here. And you already see that what happens is that this term here, the first summand in the Leibniz rule, cancels this term. Right? And then in the next term, so this will cancel with this term. And then you see this term actually will cancel with the next term in the expansion, right? By the same argument, we have this actually, I guess, if I put a minus here, then this will cancel with the next term, where we somehow multiply the Leibniz rule out the next term, the R2 will come over here. And that way all the terms will basically cancel out each other. And maybe, okay, so I guess now I already messed it up now, so I just claim that when you do that and sort of I skip my three-dimensional board work, then you get 0. Okay, compatibility with the con operator and the d operator is the following equation, which I've already written on the board, so feel free to go through this either yourself or pause the video and go through this computation. This shows that mu of the operator b applied to R0 through Rn is equal to d of mu of the same guy. That's what you have to show in order to show that it's compatible with this operator, and it's a little computation like this. And finally, you have to check that the map mu is also compatible with the shuffle product and with the wedge product of differential forms, and that is a similar computation, which at this point I leave as an exercise. Okay. What is the meaning of that mu? So immediately now we have the following corollary. If R has flat cotangent complex, same assumption as in HKR, again think smooth, and again Q is in K, let me say that again, but this is the standard assumption now, then we have that HHRK with the partial and the B operator is actually equivalent to omega star RK 0D, by which I mean it's equivalent as a DGA and as an A module in the derived sense, so meaning quasi-isomorphic. So maybe I should put a single dash here. Okay, and why is that? Proof. We always have that the composition, and by always I mean without any assumptions on R, still with the assumption Q and K, that the composition of our standard HKR map that we always had, R relative K, into the Hochschild homology groups, not the chain complex, R relative K, we always had this map. This was just induced by saying it does on one forms, it sends R0 times dr1, it sends it to R0 tensor R1 in the drum complex. That this is actually, we can map further with the effect homology applied to our map mu. Right, we can do that, and then we also land in omega star R relative K. Why is that? Well, I guess here's the homology of this complex with respect to the zero differential. Then this is just the complex itself. And this map is the identity. Why is that? It's a map of CDGAs. In degree 0 it's R, in degree 1 it's just the identity, obviously, because again, as I said, this map send it R0 dR1 to this class here, which then gets mapped to R0 times dR1 by the definition of mu. So in other words, in order to check that this map mu is an equivalence, it's enough to check that this is an equivalence. So the statement follows from HKR. So this corollary really means that mu is an equivalence precisely if the HKR map is an isomorphism. Okay, and this corollary you should basically consider as a formality statement. It tells me that the Hochschild homology as a guy with this DG module structure is equivalent to its homology, right? Namely the homology being the same, the homology of it with the zero differential. So that's really a formality statement, and this is the natural formality statement. And that's a very important result. And now I guess the reason we started talking about that is we wanted to prove our theorem A. Namely, we wanted to prove that periodic cyclic homology and negative cyclic homology are essentially given by variance of two periodic de Rham cohomology. So for theorem A, we get that, we know that periodic cyclic homology of R relative K, this is now computed by the complex. Maybe I write this as, or maybe I write like this. This is now computed as the homology of the complex. A priori it was the complex, let me write this, HH R relative K, brackets, I guess HP, we have round brackets T, and then we had this differential which was given by partial plus dB. But now this is isomorphic to the homology of this complex which is quasi-isomorphic, which is this complex. And again, by my earlier remark, I can also apply this formula to this complex. So what do I get here? I get omega star R relative K, bracket, round brackets T. And then what's the differential now? There is no partial differential because that's 0. So the differential is just going to be given by TD. And then if you just figure out what that means, this just means that this gives me the de Rham differential and this lowers T degree. But still, this is isomorphic to the two periodic de Rham cohomology. K, T, because T is actually a cycle. Okay, and that gives the proof of theorem A, and I guess similarly we get the statement for HC minus. So HC minus star with the same logic is then isomorphic to the homology of the chain complex omega star R relative K power series T with the differential TD, and then it's immediate to figure out that this is the term I gave you, which in 1 degree takes the cycles, and then because this comes from the truncation in the T variable, don't allow negative powers of T, and then I get the cohomology. Okay, and that finishes the proof of theorem A. And this shows why in characteristic 0, periodic homology is canonically two periodic de Rham cohomology, right? Characteristic 0 was very essential for this assumption, and this in fact fails in positive characteristic. And let me talk about this now. So I will have a little bit of a longer discussion about that and a little bit more precise discussion about that in the case that we work with non-affine schemes in my companion lecture. So for the moment, I'll just restrict to the easiest possible case. That's the following. The following construction. So if K is arbitrary, arbitrary is still a commutative ring, but we drop the characteristic 0 condition, then we have the Postnikov filtration tau larger equal bullet HHR on the Hochschild complex. So this is just a filtration whose nth filtered piece is just given by taking cycles in degree n and everything above and nothing below. Just a complex which has the same homology starting in degree n and 0 below. It's a filtration on the Hochschild complex. So this becomes a filtered chain complex and is compatible with all the structure. It's compatible with the B operator in the sense that the B operator, I mean, this is a filtration through A modules and leads to a filtration on HC minus, and maybe I concentrate on the case for periodic homology for expository purposes, R relative K, which is concretely given, what does this look like? Recall HPRK was computed by this double complex, so we're going to say is concretely given by tau larger equal bullet of this HHR relative K round brackets T, and then we have this differential partial plus T B. So that's a filtration of the chain complex HHR adjoint T with this guy. And that's a filtration, and thus it leads, everything is compatible with multiplicative structures and so on. It's a Postnikov filtration. That's the most canonical filtration. It's not the stupid truncation or anything. And stupid filtration in this case would also be, stupid truncation would also be compatible with product structures, but the Postnikov truncation always is. And leads to a spectral sequence, leads to a multiplicative conditionally convergent spectral sequence, leads to a multiplicative and conditional convergent spectral sequence, which goes from, I guess, the Hochschild homology R relative K, round brackets T, and conditionally converges to the periodic homology R relative K. Why is that? That's because the associated graded by definition of this filtration are just going to be the Hochschild homology group in a single degree. There's no potential for a non-trivial B operator. So in that case, you'll just get this where this is 0. Right? And then this is just going to be the Hochschild complex. Okay, good. And then this is the spectral sequence. And the next page of the spectral sequence, so I guess this is maybe depending on your exact grading, and I'll use homological Serre grading in a second, then this is maybe the E2 page of the spectral sequence. The next page of the spectral sequence, so the first differential by what I just said, the first differential in the spectral sequence you see from contemplating what the next side starts looking at, it's like the spectral sequence of a double complex. You see the next differential is going to be given by the B operator. I make that also precise in my companion lecture where I talk about the decalage of filtrations and how this gives another filtration. For the moment, let me just say that the next page with maybe should be a little bit more precise. This is my E2 page in homological Serre grading, and with E3 page given by the homology of the chain complex, which is the homology, Hochschild homology R relative K, and this is equipped with the B operator as a differential. So that, though I can take the homology of that and T, and it converges to HP star R relative K. If R over K satisfies HKR, has flat cotangent complex, So I guess for this spectral sequence, you don't even need that R is commutative, but if R is commutative and has flat cotangent complex, then this is by what we talked about earlier, this is just going to be a spectral sequence from the RAM cohomology R relative K, H star, the RAM R relative K, brackets T, and converging to periodic homology of R relative K. And this is a multiplicative, conditionally convergent spectral sequence. And you should consider this spectral sequence, and again this is E3, but there is going to be a formal device of making that into E1, that's Deline's décalage. We'll talk about that in a companion lecture, and that will, because this will in particular be important in the non-affine case. But this is the spectral sequence from the RAM cohomology to periodic cyclic homology. And that's what you should consider to be the positive characteristic or mixed characteristic analog of the statement that in characteristic 0 those two terms are isomorphic. So this basically says that the spectral sequence canonically collapses in characteristic 0, or like degenerates. There could a priori be differentials, but there aren't. And that's the statement of what we did earlier over the rationals. And now I will give you a sample example of what can happen in characteristic P. So far we've discussed the case of smooth or like L-flat algebras, and now we want to talk about our other running example in this course, namely Fp relative to the integers. And in order to be able to formulate the answer and to give the computation of periodic and negative cyclic homology in that case, I need the following definition. And that is, if R is a commutative ring, then we define the divided power series algebra. Series algebra R pointy brackets X as the completion of the free divided power series ring Rx at the filtration generated by the divided powers of X. Note, this is not an adic filtration. It's not the same as completing this guy at X. We rather completed the filtration generated by X, X to the like square brackets 2, X to the square brackets 3, and so on and so forth. That is the divided power series algebra, which we want to consider. And in general, of course, this is if R and X are both in degree 0, we will apply that to the case where R is a graded ring and where X is also an element in positive or negative degree. And then the usual convention, if you complete graded objects at elements or ideals which sit in grading degrees, what you do, you just basically, first of all, ignore the grading, complete, and then you look at homogeneous elements. Right, so I guess you only allow like infinite terms when they are like homogeneous. Okay, that's the usual convention. I guess we've sort of used that before when I wrote down power series variable algebras on positive degree or negative degree elements, that T. Same convention applies here. Okay, good. So and now with this definition we can state the result, the following proposition which we want to prove. And the result is that for R equals Fp, we have, I mean, maybe R equals Fp is a little bit misleading because it's not the same R as in the last example. But for the ring Fp, we have that the negative cyclic homology of Fp relative to the integers is, as a graded commutative ring, isomorphic to the P at X. And then we adjoin a polynomial variable X. Then we power series adjoin the X. So X is going to be in degree 2, T is going to be in degree minus 2, as usual. And then there's a single relation, namely xt minus p. So that's what hc minus is. And then we also have hp, periodic homology, hp star. I mean, I guess you can easily deduce that from this by just inverting t now. So this is going to be fp relative c. This is going to be isomorphic to the p-adix adjoint t plus minus. Then your power series adjoint the x. And then your quotient by xt minus p. But this, in this case, is too periodic, so I can also write it as a term in degree 0, where the term in degree 0 now is just the Zp power series y. And then your quotient by y minus p. That's a classical ring, so y has degree 0. And then I just adjoin t plus minus. That's just a rewriting of this term, taking into account that t is invertible. So we can basically replace the x by t to the minus 1x, which is y, and then it sits in degree 0. Okay, good. That is a rewriting of that formula. And that's the result we want to prove for the rest of the lecture. And let me, before I prove that, I want to make some remarks. So first remark is, of course, this ring, I guess this ring which stands over there, which is isomorphic to HP0. And I mean, in general, of course, HP0 is isomorphic to HC0 minus. I guess that's something which immediately follows from the definition that periodic and negative cyclic homology agree in all non-positive degrees. Right, just by the definition of inverting that element t. And so we see that these are isomorphic, and that, as I said over there, is this ring. This is a little bit of a funny ring. So this is the ring is obtained, I mean modulo this completion, which I will ignore for a second, is obtained by adjoining divided powers of p to the p, right? So I guess you could basically write this, I mean, you could replace y by p here. So you're going to adjoin divided powers of p. But that's a little bit of a funny process, because if you think about the p-adix already have divided powers for p, right? Because p to the p, I mean, this is the first non-trivial, all primes except for p are invertible in the p-adix. So you have to check that you have like p's divided powers, but what is p to the p? Well, p to the p is certainly divisible by p factorial. So I can easily define a divided power. So it already has divided powers, but we somehow neglect that fact and then freely adjoin new divided powers to p. And what's the result of that? The result is actually that we get a lot of torsion. Get torsion by this process, right? Because now I have this term y to the p, that's the divided power of p, but I also already have this divided power of p over p factorial, right? That's an element in the p-adix. And that guy is certainly now p torsion, right? Because if I multiply that with p factorial, then I'm going to have here, I'm going to get y, which is p, and here I'm also going to get p. Y to the p, sorry. And p to the p, which agree. So that is going to be p torsion. It's p factorial, or equivalently p torsion. So it's not such a pleasant ring, and in fact, leveraging this fact that these divided powers of p already exist, we have that this ring, Zp, and maybe I'm going to ignore the completion for the moment. This is actually isomorphic to the ring, which you can write as Zp adjoint Z modulo Z. Right, with Z equals y minus p. In order to write down this isomorphism, you just have to observe that for this choice of Z, you can canonically use the fact that y and p have divided powers to define divided powers of that. That gives you this isomorphism, and here you see very clearly that this is the kind of little bit complicated ring, because you adjoin all these divided powers of z, but then you quotient by z, so there's nothing which these are divided powers of anymore. Okay, so that's somewhat, I think this should somehow be considered as a warning that the result of periodic and negative cyclic homology of Fp relative to the integers is not very pleasant. And actually, somehow the upshot of this course is that the situation becomes much better if you replace negative cyclic and periodic homology by topological negative cyclic and topological periodic homology. Then somehow the situation, these divided powers will go away. We'll talk about that later, and everything becomes much cleaner and much nicer to work with. Okay, and as a last remark, I wanted to say, I guess I already mentioned that there's a relation between the Ram homology and periodic homology, and if you, I mean, here we are certainly not in a situation where we are smooth, like Fp is far from smooth over the integers, but it's still like quasi-symptomic. And then I mentioned there's this relation with derived de Ram homology, and in fact it turns out that this Hp star of P relative Z is two periodic derived de Ram cohomology. Ram cohomology. The Ram cohomology of Fp relative Z. So if you've seen that, Hodge completed two periodic derived de Ram cohomology. Okay, good. So now we'll prove that after cleaning the board. Okay, so we want to prove our result. We want to prove or compute negative cyclic and periodic homology of Fp relative to the integers. And let's recall that Hochschild homology Fp relative to the integers was given by the free divided power algebra on a single generator. So that's the one input we will use. Sorry, not divided power series, divided power algebra on a single generator, x in degree 2. And also what we want to use the spectral sequence that we just constructed, which goes from Hochschild homology adjoint power series variables. So this will go from Fp x, and now I guess I have to power series adjoint x, but in this case I can just polynomially adjoint x. It's the same, and this will converge to Hc minus star Fp relative Z. Right? And how does the spectral sequence look like? Well, let's just picture it. And I'm going to use homological Serre grading. I'm going to tell you in a second what that is. So here on this line, I'm going to have Hochschild homology. So I'm going to have here degree 0. I mean, I'm going to have an Fp. So all dots are going to be Fps. I'm going to have my Fp here. This is 1. Then I'm going to have my element x here. Here I'm going to have x squared. So x2 over 2 factorial. I guess this divided power. And so on and so forth. And here is going to be my element 2. So this is degree 2, this is minus 2. And then I have t squared minus 4, t3 minus 6, and so on. So this is how the spectral sequence look like. And in this grading, the total degree would be along these diagonals. Right, that would be total degree 0, and I guess this is supposed to be a straight line and hitting all the dots, of course. And the differential, the first differential would go, like the first differential would go 2 over and 1 up, the next differential 3 over and 2 up. So it's homological Serre grading, so immediately see, because everything is evenly generated, this immediately degenerates the spectral sequence. And so in particular, we also, I said before, the next page would be this running the B operator, but there is no B operator. There is no first differential, there's no differential at all. So this immediately collapses, the spectral sequence. So it collapses. So in other words, we know that HC star minus has a filtration, so thus HC star minus has a filtration with associated graded, or complete exhaustive filtration with associated graded given by this algebra Fp xt. And now everything comes down to figuring out extension problems, right? So there's an additive extension problem and there's a multiplicative extension problem. So a priori, I could have that it's just isomorphic to Fpx adjoint t. So in other words, that all these extensions along this line build up to an infinite product. But what happens, in fact, I mean, I guess you've already seen the answer, that these build up a copy of the p-adix. So we have to solve an extension problem here. And also we have to know that the x, we only know it has divided powers on associated gradeds. So we need to know that the x actually has divided powers. Right, so these are two extension problems that we have to solve now. And in fact, we're going to actually we're going to see that both of these problems can be solved at the same time. And how do we do that? And for this, actually, we have to use a little bit of theory about simplicial commutative rings. So the first thing is that the connective cover of HC minus, sorry, I guess I did want to write the spectrum or the chain complex, is actually can be represented by a simplicial commutative ring. Commutative ring. And to see this, actually, I want to adhere to something we do later in this lecture, namely we study a little bit more precisely what everything that we did so far means homotopically. And so there's a homotopy theory of simplicial commutative rings called animated rings. And in fact, it turns out that everything we did, Hochschild homology and so on, I mean, I guess we've already seen it for Hochschild homology, but also the con operator comes from an S1 action in animated rings. And then we can just take homotopy fixed points in animated rings. And that will again be an animated ring, and this is what HC minus really is. We'll come to that later. At the moment, we just want to import the fact that the connective cover can be represented by such. As a result, thus, by what we've seen in an earlier lecture about the existence of divided powers, thus it admits divided powers on positive degree homotopy groups. Right, thus every choice, in particular, every choice of x and t lying in the homology gives rise to a map, right? So a priori, I guess I'm confusing notation here a little bit. X and t are a priori, I guess, now elements on the E2 page of the spectral sequence. But as soon as I pick choices, which I also denote x and t, I get gives a map from the guy z brackets x t into HC star minus Fp relative z. Right, I just pick a choice of x, a choice of t, and then I get a map like this. And if we can find maps, if we find x and t in the homology such that xt equals p in HC star minus Fp relative z, then this map induces an equivalence, an isomorphism on associated gradients. Right, where we put a filtration here, which is like this filtration here. We just put these guys in the filtration coming from the spectral sequence. Can just declare that algebraically here. And if xt equals p, then this factors, I guess, then I should say, maybe I should say that better. And this map induces an isomorphism on associated gradients of the map. I mean, I guess, sorry, I didn't say that very well. So I should say here, then I get an induced map like this into HC star minus, and that then with this filtration induces an isomorphism on associated gradients. And this filtration here is complete, so we can complete here and then we get the answer that we need. That immediately implies the result. Right, so what we have to prove in order to prove our result, I mean, I guess the HC minus result, and we've already seen that the HP result would follow from that. In fact, I guess one could easily also see the HP spectral sequence would just add positive elements of T. Then it would just be sitting up here, but everything still would be even and collapse, and you'd basically do the same argument. But it also formally follows. So everything that remains is to show that we find lifts X and T, so that the product is P in the homotopy groups of HC minus. And I'll do that after cleaning the board. Okay, so how do we find such lifts? Well, and for that, let's get back to the computation. The computation of HH, Fp relative Z. So I did that in the last video, and in this video I in particular explained that when we resolve Fp, so what we have done, we have resolved Fp, we've written it as an exterior algebra over the integers on a generator epsilon, and I put a differential partial epsilon equals p. Right, and then we resolved Fp. I mean, I guess we just fit that DGA into the cyclic bar complex, and then we got this double complex, and this element X, we had this element X, which we then just declared on the chain complex level as B epsilon. Or I guess it was also like in the picture I had on the board, it was epsilon tensor 1 plus 1 tensor epsilon, but it also then I computed that it's B epsilon. Right, and the point is that the partial of X was 0. So X was a cycle, and also we've seen that Bx is actually, I guess we haven't seen that Bx is 0 on the nose in the complex. I should maybe write in the complex of this guy, Fp relative Z, right? So this is just the CDGA, which is obtained by replacing Fp by this and then running the cyclic bar complex. But I mean, it immediately follows from this equation because we know B squares equal 0. So thus, we immediately get directly that in Hochschild homology, in HH, Fp relative Z, we have that X is a cycle, representing the element X in homotopy, also called X. Right, that was kind of the way we represented that element in homotopy. I guess this is maybe not that we get that, but that was maybe how we obtained this element X in homotopy. I just wanted to recall that. But now the point is that Hc minus, as we've seen earlier, of Fp, this could be calculated by the chain complex where we just put HH, the chain complex HH, Fp, Z, and then we have adjoined this element T, and then we put this differential. And what is the differential? Well, the differential here was just given by partial plus Tb. Right? And now let's see what happens with our element epsilon. So what happens with our element epsilon? So epsilon is going to be an element in here. And what is the differential evaluated on this epsilon? Right, so the differential evaluated on that element epsilon, this is now given. I mean, we just have to calculate what is partial of epsilon. That was p, right? That equation still holds. This is p plus, and what is tb of epsilon? Well, we've just seen that b of x, I mean b of epsilon is x, so we get tx. But now the point is that t and x are both cycles in here, and we get the relation that p is equal tx in the homology. Right, that relation now immediately follows because we found a reason why it holds. It's the boundary of an element. And that proved that we have this relation there, and that concludes the proof. Okay, I want to finish today's lecture by 2 short remarks, or semi-short remarks. So the first remark is that one can, in fact, prove a little bit more, but that is a little... Well, let me just say one can also deduce this whole result, this computation, using that Hochschild homology Fp relative z together with the partial and b is quasi-isomorphic to the following guy. So I've just put epsilon and adjoint an x here. That's a graded commutative ring, and here I want to put a differential which makes partial epsilon equals p and partial x equals 0. And then I want to put a con operator on that where b epsilon equals x and bx equals 0. I guess when I write that also this should hold for all divided powers. And I guess we've basically used in our proof here this result not for the full guy but for a truncation of it. We really only needed it for x and epsilon. But one can in fact, I think, re-deduce from this result that this is true, and to be honest, we were trying to find a direct argument for that, and it turned out to be a little bit hard. It's also like, I guess, things become a little tricky here because of the expressive power of these kind of mixed complexes. I told you before that really the B is not fully compatible with the multiplication, and we will talk about that later when we come to animated rings. At this point it's a little hard to somehow leverage this equivalence, but once one had that, one can immediately just apply the formula with the adjoint t and immediately just gets the full calculation of what hc minus and hp are. So maybe at this point we could just take that as an experimental observation, and we'll talk about that a little bit later. Okay, that was one remark that I wanted to do, and the other one is, I guess I haven't really talked about cyclic homology, and I will not in this lecture. Let me just say that one can construct long exact sequences coming from cofiber sequences of the form hc star minus r relative k. Then I have hp star, that is the canonical map, which we have by definition. And then it turns out that hc star, I guess, minus 1 of r. It's the next term here. Is it minus 1? I hope it's minus 1. And then I guess the next guy. hp star plus 1, r relative k. And here I continue to the next hc star minus 2 r. And I guess, okay. So, and in fact, I mean, this is not very hard. In fact, I mean, as I said, you can, on the chain complex level, basically, if you want, you can show that this is a fiber of the canonical map here. or like this is a distinguished triangle in the derived category, and then you get these long exact sequences. And if you want, you can use these long exact sequences to calculate HC in all the cases we care about. The main point is that while HC minus and HP are like rings, HC is not. So you should think of it as being an ideal sitting in here. So you might want to express that as a module over this guy if you want to sort of give nice or like pleasant algebraic ways of thinking about that. But of course, I mean, it might be a good exercise in the cases that we've calculated all of that, try to calculate it, especially in the HKR situation. Okay, so that's what I wanted to say for today about periodic homology and negative cyclic homology. Thanks for watching, and hope to see you soon in the next video and in the companion video. So recall, I wanted to make a companion video where I talk about the non-affine situation and in which all of that eventually becomes way more meaningful. This companion video will not be required necessarily for everything we do afterwards, but I think it might help, at least if you are somehow interested in non-affine schemes. Thanks very much.